Chapter 4, Atoms and Elements. Here we are going to begin to learn the language and symbols of chemistry, a very important basic chapter. Let's imagine ourselves at a place like Tiburon, which is on a peninsula that reaches out into the San Francisco Bay. As we look around, we can imagine the seaside rocks. They're composed mostly of silicates, and the air contains the nitrogen and the oxygen molecule. The seaside air may also contain substances called amines. The amine shown here is triethylamine, and it's emitted by decaying fish. And triethylamine contributes to the fishy smell of the seaside. So in this setting, we begin to imagine us surrounded by molecules. To get an idea how small these atoms are, imagine this: for every atom within a small pebble, if the atoms were the size of the pebble itself, then the pebble would be larger than Mount Everest. Atoms and elements. Atoms compose matter. Properties of atoms give the matter its properties. An atom is the smallest identifiable unit of an element. An element is a substance that cannot be broken down into simpler substances. There are about 91 different elements in nature, and these are made up of 91 different kinds of atoms. Scientists have succeeded in making about 20 synthetic elements that is not found in nature. A Greek by the name of Democritus first conceived and coined the word atom. In Greek, at about 460 to 360 BC, you see recorded ideas about atoms. And it was Democritus who suggested that if you divide the matter into smaller and smaller pieces, you'll end up with a tiny, indestructible, indivisible particle. Democritus called these atomos, or atoms, meaning indivisible. And he is the first person to record that matter is composed of atoms. On the right, we see a picture of Democritus with Diogenes, and as imagined by an artist. So the early history, the first idea and coining of the word atom. The next person to build up a basic atomic theory was John Dalton. It was about 1808, more than 2,000 years after the Greek idea of Democritus. He formalized a theory that gained broad acceptance. His ideas are each element is composed of a tiny indestructible particle. All atoms are a given substance, have the same mass and other properties that distinguish them from atoms of other elements, and atoms combine in simple whole number ratios to form compounds. Along about 1856-1940, a scientist called J.J. Thomson, an English physicist, found out that atoms have parts. And he did this by his discovery of a particle called the electron. He found out electrons are negatively charged, and they're much smaller and lighter than atoms, and he proposed that atoms must contain somehow a positive charge that balanced the negative charge so that the entire atom was neutral. He's famous for what's known as the plum pudding model of the atom. In this model, the black kind of positive mass part is like the pudding, and the negative electrons are embedded in there like plums in plum pudding. This was his first idea of what the atom might look like. The idea or model for an atom was further spelled out by a scientist called Ernest Rutherford. And Ernest Rutherford did what is called the gold foil experiment in 1909. And what he did is he took radioactive substance that emitted alpha particles, and he lined them up and shot them at a thin piece of gold foil. What he found is most particles pass right through the foil. A few were deflected slightly, and then very few just came right back, almost directly back. What are the implications of this experiment? Well, first of all, most of the atom's mass and all of its positive charge must be in a very small core called the nucleus. And this would enable the light particle to fly right straight back at you. Most of the volume of the atom was empty. That's why most of the alpha particles went straight through. And the number of negative charge particles outside the nucleus must be equal to the number of positive charge particles inside the nucleus. So the atom is electrically neutral. This image of the nucleus here, and then the electrons placed far apart outside. So the nuclear model shows that the atom is mostly empty space. Just a brief summary to remember about electrical charge. If you have a positive and a negative charge, they attract. Two positive charges, they repel. Two negative charges, they repel. A positive and negative, positive, negative, there is a repulsion occurs. Positive and negative charge cancel. If you have a plus one and minus one, you end up with a zero neutral charge. So in the properties of the atom, within the atom we have these particles. We have proton, neutron, electron. Important to know that the protons have very similar mass. Not exactly the same, but very similar to 1.67. And then that's in kilograms. If you state that mass in atomic mass unit, it's 1.0073 and 1.0087. And the charge of proton is +1, neutron is neutral. Then we have the electron, which is very, very much lighter. Actually has 3.00055 AMU, but it has a -1 charge. So these are the sub-elements are defined by the number of protons they have. It's the number of protons in the nucleus of the atom that identifies it as a particular element. The number of protons in the nucleus of the atom is called its atomic number, and is given the symbol Z. For instance, helium has 2 protons in its nucleus. Its atomic number is 2. Aluminum has 13 protons in its nucleus, and its atomic number is 13. The periodic table lists all known elements according to their atomic numbers. These are the atomic numbers. You can see them right here on top of the symbol Z. And you see it begins with 1, it continues with 2, 3, 4, 5, in that order. We have they're arranged in order of atomic number. How do we get the names of the elements? Well, most chemical symbols are based on the English name of the element. Some symbols are based on Latin names. For instance, the symbol for potassium is K, and it comes from the Latin word for potassium called kalium. Symbol for sodium is capital N, lowercase a. It's from the Latin natrium. Additional elements with symbols based on their Greek or Latin names include the following. Lead is from plumbum, hence the symbol is Pb. Mercury is from hydrangea, and it's Hg. Iron is from ferrum, which is Fe. Silver is from argentum, Ag. And tin is from stannum, Sn. And copper is from cupron, Cu. So this explains why you have rather strange letter symbols for an element that in English doesn't even look like its symbol. Origins of names of the element also comes from various different sources in the world. Early scientists gave newly discovered elements names that reflect their properties. For instance, argon is from the Greek word argos, which means inactive, and it refers to argon's chemical inertness. Other elements are named after countries. Polonium after Poland, francium after France, americium after the United States. Other elements are named after scientists. Seaborgium, many others. Every element's name, symbol, and atomic number are included in the periodic table inside of the front cover, and alphabetically listing is inside the back cover of this book. Use them for a reference. Marie Curie, a Polish chemist, is the one who discovered curium, and so the element curium with the symbol Cm is named after her. She discovered 2 other elements, and she won 2 Nobel Prizes for her work. Radium and polonium are other elements. Bromine originates from the Greek word bromos, which means stench. Bromine vapor is a red-brown gas, and it has a very strong odor. Looking for patterns, the periodic law and the periodic table. We owe much of this to Dmitry Mendeleev, a Russian professor of chemistry. He proposed from observation, when the elements are arranged in order of increasing mass, certain sets of properties occur periodically. The color of each element represents its properties, and if you arrange them in rows so that the similar properties align in the same vertical column, then you begin to get a periodic table similar to what Mendeleev arranged. So all of these have the same kind of properties. These the same, these the same, these the same. So the columns represent elements with similar properties. What are some of the patterns? Well, one of them is, what kind of substance are they? Are they a metal? You can see that most of the elements in the periodic table are metals. Are they a non-metal? You see them in the green, with the exception of hydrogen, which is a non-metal. And then you see the metalloids, which arrange themselves kind of along this diagonal step-like thing. Metals, they occupy the left side of the periodic table. Metals are good conductors of heat and electricity. They can be pounded into flat sheets, that's malleable. Metals can be drawn into wires, ductility. Metals shiny, that's lustrous. And metals tend to lose electrons when they undergo chemical change. Good examples are metals are iron, magnesium, chromium, and sodium. Nonmetals occupy the upper right side of the periodic table. The dividing line between metals and nonmetals is the zigzag diagonal line that runs from boron to astatine. Nonmetals, they have more varied properties, and some are solids at room temperature, while others are gases. As a whole, nonmetals tend to be poor conductors of heat and electricity. Nonmetals tend to gain electrons when they undergo chemical change. Good examples of nonmetals are oxygen, nitrogen, fluorine, and iodine. Metalloids, they lie along the zigzag line, and they're also sometimes called semimetals, and they also are called semiconductors because they are of their intermediate electrical conductivity. This property makes semiconductors useful in manufacture of electronic devices that are central to computers, cell phones, and other modern gadgets. Silicon, arsenic, and germanium are good examples of metalloids. We also divide the periodic table into 2 kinds of groups, main elements and transition elements. The main elements are shown in yellow, and they are also, the rows and the columns have the letter A behind it. So they're main elements, the main group elements, or sometimes called representative elements, and then the blue are said to be the transition elements, and they're all metals. they have B after their column name. We even have family names for elements. Those, remember, that are in a vertical column behave like, and so we consider them a family. We have the alkali metals in group 1A with the exception of hydrogen. And we have the alkaline earth metals in group 2A in those orange color, the transition metals, and we have the halogens in blue, and we have noble gases in a pale green. So we have transition elements, and we have the lanthanides, which of course they follow after lanthanum. Here's 57, 58, or the actinides, which they follow after actinium, which is 89, 90. The alkali metals are shown here in group 1A, and they include, I'll say the names for you, lithium and sodium and potassium, rubidium and cesium. The alkaline earth metals are in group 2A, and I'll show you them and pronounce their names. Beryllium, magnesium, calcium, strontium, and barium. The halogens are in group 7A, and they are all diatomic. In other words, they exist with like F2, O2, that sort of thing. They are fluorine, chlorine, bromine, iodine, and astatine. The noble gases, including helium, are used in balloons. They're very inert, and they are helium, neon, argon, krypton, and xenon. An ion is a charged particle, and they are gained by either an atom losing electrons or gaining electrons. In chemical reactions, atoms often lose and gain electrons to form ions. The positive ions are cations. The negative ions are anions. You see the N and the negative, anions. The charge of an ion is shown in the upper right corner of the symbol, and ions are usually written with the magnitude of the charge followed by the sign of the charge. Here's an example. Lithium may lose an electron and become lithium with its +1 up here. The charge of an ion depends on how many electrons are gained or lost. So the number of protons that you have minus the number of electrons gives you the charge. For the lithium ion, you have 3 protons and only 2 electrons, so the charge is +1. Some atoms gain electrons. For instance, fluorine gains electron, becomes fluoride, or F-. So the charge again is still the same formula, the number of positive protons minus the number of electrons. The number associated with the letter A above each main group column in the periodic table, 1 through 8, gives the valence of the electrons in the element in that column. The key to predicting the charge acquired by an element in its position in the periodic table relative to the noble gases. Main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. Looking at this periodic table, I'll show you how you can look at the table and get what would be the charge of the ion. All of these in group 1A tend to form a +1 ion. All of those in 2A tend to form a +2 ion, because by losing 2 electrons, it gives the same number of electrons as the preceding inert gas. All of those metals in group 3A tend to form a +3 ion. However, among the nonmetals, they tend to pick up electrons to reach inert gas number. So oxygen is in 6. It needs 2 more to get the 8 electrons as the inert gas. So it's a -2. All of these in group 6A are -2 ions. In 7A, they all form -1 ions. Isotopes. When the number of neutrons varies. It's understood that for an element it always has a fixed number of protons, but the number of neutrons can vary. Different atoms of the same element may not necessarily have the same number of neutrons. Those atoms that have different numbers of neutrons but the same number of protons are called isotopes. And all elements have their unique percentage in natural abundance of isotopes. Let's take the example of neon. Neon occurs containing 3 different isotopes. Neon 20 with 10 protons and 10 neutrons, neon 21 with 10 protons and 11 neutrons, and neon 22 with 10 protons and 12 neutrons. This occurs regularly with a 94% of one type, and the other percentage are the other types. The neon 21 is only 0.27%. The neon 22 is only 9.25%, and the neon 20 is the most part, is 90.48%. How do we write the symbols of an isotope? Well, in general, the element has the symbol for the chemical element is here where this X is. The upper preceding superscript is the mass number, and the lower subscript is the atomic number Z. Of course, you'd have any charge here. For example, these elements of neon are neon 20, neon 21, and neon 30. That's their mass number A. The mass number is the sum of the number of protons and neutrons. So the number of neutrons in an isotope is the difference between the mass number and the atomic number. The atomic number of each element listed in the periodic table represents the average mass of that atoms that compose the elements. So the atomic mass is different than the mass number. It's listed in the periodic table, and it's an average of the natural abundance. For instance, naturally occurring chlorine consists of 77.77% chlorine 35, which has an actual mass of 34.97, and 24.23% of chlorine 37, which has an actual mass of 36.97. So the average weighted atomic mass of chlorine you'll see is this transferred to 0.755, the decimal, times its mass plus the decimal percent, the percent transferred to decimal of this mass, and then that combined gives you 35.45. That will be the number you'll see as the atomic mass of each element, of chlorine element. Example, how do you calculate this? Gallium has 2 naturally occurring isomers, Ga69, which has 68.9256 AMU, and a natural abundance of 60.11%, and Ga71 with a mass of 70.9247, and natural abundance of 39.89. Calculate the atomic mass that will appear on the periodic table for gallium. This is done by, first of all, converting the percentage to the decimal percent. Then you use the fractional abundances, which are these numbers, or decimal, and the atomic masses of each isotope to compute the weighted atomic mass from natural occurrence. So here's the 0.061, the decimal percent, times its mass, plus the 0.3989 times its mass, and the computation turns out to be 62.72. Check it out. If you see gallium on the periodic table, its atomic weight will be given as 69.72. So this gives you a brief overview of the elements, and the periodic table is an important way to organize the elements, and this should help you with the chapter and particularly help you with the pronunciation and symbols.